The Consultative Committee for Space Data Systems, CCSDS O3K standard, is paving the way for a new era in space communication by establishing clear parameters for optical transmission in space. This standard focuses on technical specifications of the transmitted optical signal, ensuring interoperability and efficiency across space missions. The standard defines a specific frequency range for O3K transmission, varying from 191.3 to 195.9 terahertz, with a center frequency at 193.1. This translates to a wavelength range of 1530.33 nanometers to 1567.30 nanometers, aligning with the C-band in optical communications. A tight tolerance of ±10 GHz ensures minimal frequency deviation, critical for reliable communications. Laser line width and energy concentration. The laser line width, a measure of the range of emitted wavelengths, must be less than 10 GHz for optimal signal quality. Additionally, 95% of the laser energy should be concentrated within ±20 GHz of the center frequency, ensuring a focused and efficient transmission. Modulation, OOK, and post-position modulation. The standard specifies on-off keying as the primary modulation scheme. This simple technique represents binary 1 as the presence of light and 0 as absence, as we saw before. Interestingly, while the standard focuses on OOK for physical layer transmission, it is based on post-position modulation signaling. This means that the information is encoded on the position of the light pulses, which are then transmitted using OOK. The pulse timing jitter, which refers to the variation in pulse timing, should not exceed 10% of the slot width. This ensures consistent signal timing and improves receiver performance. The slot width, the time duration allocated for each bit, is flexible and can be chosen from a range of values between 0.125 nanoseconds and 512 nanoseconds, allowing adaptability to different data rates and mission requirements. Extinct ratio. The extinct ratio, the ratio between the mean on optical power and the mean off optical power, must exceed 10 decibels. This ensures a clear distinction between two states and improves signal detection. In conclusion, the CCSDS O3K standard is a critical framework for the development of future space communication systems. By defining the characteristics of the transmitted optical signal, it ensures interoperability, reliability, and efficiency, fostering a standardized approach to optical communication space. Free space optical communications offers numerous advantages, but its Achilles heel lies in the sensitivity to weather conditions. Fog, rain, and snow can significantly impact the performance of FSO links. Let's delve into how fog, in particular, affects free space optical communications. Fog particles are comparable in size to wavelength used in free space optical communications. This leads to three primary phenomena. Absorption, when fog droplets absorbs a portion of the laser beam energy, weakening the signal. Scattering, the droplets scatter light in various directions, causing some of it to deviate from the intended path and leading to signal loss. Reflection, a fraction of the light is reflected back towards the source, further diminishing signal strength. To quantify these effects, rely on key atmospheric metric, visibility. This is the distance a light beam can travel before its intensity drops to 2% of its original value due to atmospheric conditions. As illustrated in the images and data on the slide, for example, for thick fog conditions, visibility is severely reduced, leading to high specific attenuation. This means the signal strength weakens rapidly over short distances. For moderate fog, visibility around 500 meters, visibility improves slightly, but attenuation is still substantial, impacting link performance. For heavy rain, while not severe as fog, rain still causes notable attenuation. And for very clear conditions, in ideal conditions, atmospheric coordination is minimal, enabling optimal FSOC performance. Understanding the relationship between visibility and attenuations allow FSO engineers to design systems that can withstand varying weather conditions. Techniques like adaptive optics, power control, and coding can mitigate the effects of fog and other weather phenomena, ensuring reliable communications even in less than ideal environments. In conclusion, while weather presents challenges for free space optical communications, a comprehensive understanding of atmospheric effects and the implementation of appropriate mitigation strategies can enable robust and resilient FSO links.